resolution, and then the repeatability, which means if we do the measurements on this material today, can we repeat it again and again without having any problems or without having any variation in what we have observed. So over the last maybe 20 or 30 years, the material scientists have been blessed by a large number of experimental techniques. These techniques include electron microscopy, and this includes the scanning electron microscopy. This is high resolution electron microscopy to be able to visualize things up to the nanometer scale. Transmission electron microscopy, which is sometimes referred to as the TEM, and sometimes there's a new version called as well the EFTM or FTM, which is the energy filter TM. There's another electron microscopy technique called electron backstatic diffraction, EBSD, and again all of these can be used to measure the material structure. X-ray diffraction is a very useful tool, and it has evolved from lab X-ray, so you can measure things in the lab, to measuring them in particle accelerators, which are known as the synchrotrons. So the synchrotron is essentially a big particle accelerator that uses to accelerate electrons or positrons to try to generate X-rays which are of very high resolution, of less than 0.2 angstroms, really high resolution X-ray. There's a number of other techniques which includes DSC, diffraction scanning calorimetry, atom probe, AFM, and so on. But then there are always limitations that are occasionally and unintentionally forgotten about this. When you are a young student with limited experience about how you can characterize the microstructure, you may forget unintentionally, or you may occasionally forget that these microscopes and these techniques, they have limitations. These limitations are the following. The first one is what people refer to as the specimen preparation artifact. When you're trying to prepare a specimen to observe it under the microscope, you are putting a personal element here, you're trying to prepare it by yourself. And as such, you may be introducing defects which are not present in the material while you are preparing it. So always specimen preparation is an issue. How you handle the specimen, how you put it under the microscope is of great importance. The second limitation is the sampling volume or area. I mean, this is all about the statistics of what you're measuring. So if you're measuring only a 1 millimeter by 1 millimeter spot on a big specimen, then you have to be sure that whatever you're measuring is going to be statistically representative of the entire area that you're measuring. Also, when you're using techniques like lab X-ray, then you need to know that you're only measuring the surface. Whereas if you're using high energy X-rays, then you're measuring in transmission. So there's a difference between sampling the surface and sampling inside the bulk of the material. Always when you do measurements as well, you have to use a mathematical model to verify what you have measured. So when you do X-ray measurements, you have to use a mathematical method called Rietveld refinement. And Rietveld refinement doesn't come without errors. You have mathematical errors that can happen when you are trying to fit this material. Similarly, when you try to use other methods as well, you may have errors that come with these methods. So you have to be careful that when you are reporting a result, you have to report as well the typical error that may happen because of this technique. And then there are two other parameters. One of them is that you need to be using physically and chemically sensible fitting parameters. So if you're trying to fit certain crystal structure, then you have to make sure that this material has this specific crystal structure and it can be fitted properly using this model. And finally, the most important one actually is that you need to be aware about the resolution. Resolution is defined as how fine a detail can be resolved. So before you start any experiment using electron microscopy, try to consider these 5 parameters and bear them in mind before you move any further. Right. This all puts us all material scientists and nanotechnologists into the size scale problem. And so we need tools, we need media to be able to view the structure. Okay? So if you look, there are microscopes, for instance, there are light microscopes, optical microscopes, and they use waves. In that case, it's electromagnetic waves to visualize whatever we're seeing, right? So this is one of the main requirements for a microscope. The second thing is that you need to have a microscope of an appropriate resolution. This resolution, as I mentioned earlier, is defined as it's a measure of how fine a detail can be detected in the material, so how fine you can distinguish between the details inside the microscope. And then you also need to be able to distinguish adjacent objects as separate. So when you look into two needles next to each other, and you need to have the right resolution to say that, oh, these needles are 0.2 nanometers apart or 0.1 micron apart. So this is again is one of the definitions of resolution. Okay, so in terms of the physics of resolution, so this is an example of a sine wave. It's a typical wave that describes most of the electromagnetic waves, and as you can see, that we refer to the distance between the peaks, so the distance between consecutive peaks as the wavelength, lambda, and the distance between successive troughs, which is the base of the peak. I don't know if you can see my pointer while I'm pointing at things. So this is the trough, and this is the peak. So the distance between two separate peaks is called the wavelength. The resolution in our definition is defined as half of the wavelength, lambda over 2. This specific example talks about electromagnetic waves, so you can see that the speed of light, which is c equals to lambda times nu, and nu is the frequency. So to make this a small exercise, if we look into a number of features, like things like aluminium lattice, so if you want to look into an aluminium crystal structure, if you look into the fetus inside a pregnant woman's, and also if you want to look into a speeding car, brains and so on, or atoms, you need to have certain features or certain waves to be able to view it. In that case, it's light or radar or lab X-ray or sonar or something else. So you can see that if you want to measure the aluminium lattice, then you can use lab X-ray, because the size or the wavelength of lab X-ray is 0.1 nanometer, which is less than the half of the aluminium lattice, which is 0.4 nanometer. And this way you can visualize the aluminium lattice. If you want to see the fetus, then sonar is good, because sonar can distinguish features within 1 to 10 millimeter of resolution. If you want to see the speeding car, then the radar can be used as well as a good means of looking into that. And then if you want to see the grains, then you can use simple light microscopy. So simple optical microscope like the one you've used in your high school is good enough to look into the grain structure. But then if you want to see the individual atoms, then you need something else. And then I put some question marks, as you can see. So moving on. Now, in order to be able to see, as I mentioned earlier, we need waves. And for that, if we look into the electromagnetic spectrum, this is an example of the electromagnetic spectrum, showing all the electromagnetic waves that we have, and it also shows the visible light spectrum. So the visible light spectrum is quite limited. It's only between 400 to 750 nanometers, which means that the wavelength of visible light is approximately somewhere about 500, 600 nanometers. So the smallest thing you can see with an optical microscope is probably about 300 nanometer maximum. This is how far in an optical microscope. But then there are other things, like there's ultraviolet, there's X-rays, there are radio waves, and these radio waves and that kind of waves are the ones that are used in sonar or the radar or so on. As you can see, there's the radar there. And there's also gamma rays. And it can be quite, even though gamma rays have very small wavelength, it will be quite challenging to make a microscope using gamma rays. So we're not going to use gamma rays, but we're going to look into other alternatives. How we can use electromagnetic waves, or we can use some sort of a wave to be able to see fine details. And this brings us to the subject of this talk, which is seeing by electrons. And to start, I have to give you a brief history of the electrons. So just to know a bit about electrons and their history. It all started with J.J. Thomson in 1897, a British scientist who discovered the electron, and he got Nobel Prize later on after that. And then another scientist, Robert Millikan, who discovered the electron charge, or was able to calculate the electron charge. He's an American scientist, and he got Nobel Prize as well for the same achievement, to discover the electron charge using the oil drop experiment. Possibly, if you have done Egyptian Sanawiyya Amma, you'll remember J.J. Thomson and Robert Millikan. Both of them, I think, are featured in the physics syllabus. And then later on in 1923, a French scientist, de Broglie, discovered something which is known as the dual nature. So his point of view was that the particles, they can behave in two ways. They can behave as a mass, and they can also behave as a wave. And he came up with this famous equation, which says that the wavelength lambda is equal to Planck's constant h divided by the momentum, which is mv. And this means that if you speed up a certain particle with a very high speed, even though it has a very small mass, if you speed it up really quickly, then you can get a very small wavelength. And when you get a very small wavelength, you can see things using that. Okay? I always try to use this example that imagine if you have a large number of people and you speed them up very fast, very, very fast, then if they hit a wall or something like that, then you should be able to see the wall shape. Or if they hit a statue or something, then you'll be able to see how it looks like. So this is the concept of the dual nature. All the particles, they have dual nature, a particle and a wave. And then after that, or before that even, Albert Einstein, he developed in 1905 the special relativity. And in that special relativity, without going into too much details, his idea was that if you speed up the particle with a very high speed, so if the particle moves with a very high speed, and in that case the speed is v, and v is comparable to c when c is the speed of light. So if you imagine v being very high, then this will approach unity, and this value gamma will be very high. And the concept is, if you make a particle speed up with a very high speed, then its mass will increase. So believe it or not, if you speed up if something speeds up very fast, its mass will increase. So you multiply the gamma factor by the original mass, m naught, and then you get the relativistic mass. And then this relativistic mass, if you put it into that equation, then you'll be able to calculate the gamma, the lambda, the wavelength. So in theory, if you speed things, if you you can even get